Okay. For this part, we focus on the rotational motion, okay, and also one important application, the motion under gravitation. So for the motion under gravitation, you know that we try to study the motion of satellites or planets. They are rotational motion around the, like satellites is a rotational motion around the Earth. Planets, they're moving with a rotational motion around the Sun. So, okay, so they are the case of the rotational motion. For the rotational motion, first, let's think about the rotational motion for particle. Okay, it's also called the circular motion. Okay, here, by the way, I want to talk about the difference between the rotation and circular motion. Okay, in our in the simple usage, we don't we think that they're almost the same thing, but they are different. Okay, do you know what's the difference between the two terms, rotation and the circular motion?
Circular motion as a fixed point, rotation is just on the center mass.
In fact, the difference comes from with if you only consider a particle. Okay, so for particle, like if you have some center here, and you have particle, it moves like this way. It's called the circular motion. And the rotation is larger than that. So circular motion is part of the rotation. So this is also called rotation. But rotation also includes this kind of motion. Think about if you are not talking about particle, okay? If you are talking about rigid body, okay? So the rotational motion may be the whole stuff rotates around some point here. But it's not necessary to be the center of mass. It can be rotate about any point. Like say it can rotate about this point here. So it's not center of mass. Okay. Of course it will be quite complicated. So both of them called the rotational motion. This is rotation, this is rotation. And circular motion refers to only this situation. Okay. Small particle moving around somewhere else. Okay. And rotation can be a large object rotate about any point, about the center, about the edge, or rotate about somewhere outside of the object. Okay. Now, first look at the circular motion. A small particle moving around somewhere else. Okay. So if we have particle, we know that in principle, if we want to study the motion of a particle, we want to establish a coordinates. Okay, here are the Cartesian coordinates. So we study the position change horizontally and the position change vertically. So basically, we want to study the position x and y, right? So in the Cartesian coordinates. To study the motion, we want to study the change in x and change in y. And for circular motion, you can see that this Cartesian coordinates description is quite complicated. like say if you start from here to here, the y position will increase, right? But the x position will decrease. And from here to here, y position decreases, x position decreases. Okay? And from here to here, y position decreases, but x position increases. And from here to here, both y and x position increases, right? So the circular motion and different parts, their change in horizontally and vertically will be totally different. So it's not good to use the x and y position to describe the motion of this kind. So we can change to use another kind of description. Okay, I don't know if you have learned this. I think it's called the polar coordinates. Okay. So instead of using x and y to describe the position, you can also use the radius r, okay, and the angle theta here to describe the motion. That's called the polar coordinates. It can be applied to any kind of motion. Like say if you have some general motion like this. In Cartesian coordinates, so at this point, you have like the x initial here, and this is y initial, right? And at this point, so this is y, this is x, so you can find out the position for different points along the motion. And if it's Cartesian coordinates, polar coordinates, you can still do the same thing. If you have the same kind of motion, here is the initial point, here is the final point. So with the radius and angle, this is origin, right? So this is your initial radius r0, and this will be your initial angle theta naught. Okay. And then at your final point here, then this is your final position r final, and this will be your final angle r theta. Okay. But again, the two numbers, a pair of numbers r0, theta naught, r and theta can specify the initial position and final position. Okay. And in fact, this one is a better description in general, because then this arrow you can see exactly the same as our displacement arrow, okay, the vector we introduced before. So this in fact is the better description. But now, it's even better here. If you look at the circular motion, okay, and so for example, it starts from here, that's our initial point, that's our final point. So the vector, okay, so the radius, initial radius is this one, this is the initial angle theta naught. The final radius r is this one, and this is the final angle. So this is r0, then this is r. For circular motion, you can see there is an important feature. It's a circular motion, so anywhere the radius will be the same, right? So r0 will be the same as r. For the whole motion, the radius doesn't change. So you don't have to worry about that. The only quantity you need to worry about is the angle. So you only need to start with the angle change. Okay. So that simplifies a lot. So kind of to change the two-dimensional motion into a one-dimensional motion, you only need to start with the angle change. So then, to describe the motion, we introduce the so-called angular position. Okay, this theta, we give it a name, angular position. It's just an angle to specify the position of the particle along the circle. So theta, and okay, so here we want to introduce angular position. It's an angle, but we don't want to use degree to measure the angle for this part. We want to use the radians. Okay. The radian. So the radian comes from this kind of definition. How can we specify the angle? If we notice that any angle can be specified for different circle like this way. If you have this angle, and if you have another circle, larger circle, okay, you will see that the angle can be specified by some ratio. Because if you have a large circle, then the arc length spanned by the angle will be larger. So this is the arc length for a small circle. And this is the arc length for a larger circle. It will be different, but on the other hand,